In this lecture, we're going to go over the finite element method for a continuous domain. Everything we've done up until this point has been for a discrete domain. So these were for systems that weren't governed by differential equations. So now we're going to look how to solve systems that are governed by differential equations. So in the finite element method, a given domain is viewed as a collection of subdomains. Over each subdomain, the governing equation is approximated using a variational method. We do this because it's easier to represent a complicated function as a collection of simple polynomials where the individual segments fit together, ensuring that the functions and sometimes the derivatives are continuous at our points. For example, if I draw a curve, this is my curve, u of x. I can break this up into little chunks and be like, all right, this is u1 of x, and it looks like this. I can say this is u2 of x. I can say here's u3 and I could keep going on and on and on. My equation u of x would be equal to the sum from 1 to n of my approximation functions. So the finite element method or finite element analysis, whichever way you want to call it, has three distinct features that make it superior to others. The first is a geometrically simple domain can be represented as a collection of, a geometrically complex domain can be. So the finite element method has three distinct features that make it superior to others. First, a geometrically complex domain can be represented as a collection of geometrically simple subdomains. So for example, say this is my domain, and my domain has a symbol omega. My domain has a boundary gamma. I can say a similar, what I'm saying is say here's my same shape, but this time I'm going to break it up into geometrically simple shapes where each one is its own little subdomain. I still have my boundary, and I still have things crossing the boundary. What I want to say is that my original domain, omega, is approximately omega h, which is the sum of my individual elements. Second, it's over each finite element, algebraic equations and other quantities of interest are developed using the governing equations of the problem. And lastly, the relationship from all elements are assembled using inter-element relationships. So what do I mean? Well, we're going to approximate the perimeter of a circle. So step one in the finite element method is to discretize our system. Say I have a circle with a radius r. I'm going to break that up. Instead of a circle, I'm going to make it 5 lines. Each of our 5 lines is a subdomain, and they're called elements. So here I have 5 elements. The length of the elements do not have to be the size. That's called a non-uniform mesh. If all of the elements are the same size, you have a uniformed mesh. So the next thing we do is we develop the element equations. In the element equation, so we isolate each element from the rest of the domain and we figure out their properties. For example, we have the length of each element. And for our circle, the length of each element is going to be 2 times our radius times the sine of 1/2 theta. The next thing we do is we assemble the element equations to form a solution. This is where we're assembling our global stiffness matrix. So the perimeter of a circle is obtained by assembling the elements in a meaningful way. In this example, the elements are based on the idea that the total perimeter of a polygon is equal to the sum of the lengths of the individual elements. So we're going to say our perimeter is equal to the sum from e equals 1 to n of the length of our elements. The last step is to look for convergence and do an error estimate. In our simple problem, we know the exact solution is our perimeter is 2 pi r. We can then approximate the error in the approximation and show that the approximate solution converges to the exact solution in the limit when n goes to infinity. So again, this was a very simple example of the finite element method. What we're going to do now is look at the derivation of element level equations. So unlike in other methods, the finite element method algebraic equations are developed on a finite element instead of the domain as a whole. So we're going to do it on the individual elements and then put them together. This is going to result in the equation in the matrix form. We're going to get to the matrix form of our stiffness matrix times our unknowns are equal to our forces. So that is the finite element method of our original equation, and that's what we're going to strive to get to. The derivation of a finite element equation involves 3 steps. First, we construct the weighted residual form or the weak form of a differential equation. Then we assume an approximate form of the solution over a typical element. And then we derive the finite element equations by substituting the approximate solution into the weighted residual or weak form. We're going to develop the weak form, and we're going to use the weak form in this class, and so we're going to develop the weak form in our next video.